Hey guys, in this lesson I want to go over population ecology and get into our lessons about populations and how they change. Talking about population dynamics, a population is all of the individuals of a species that live together in an area. The demography is the statistical study of populations. It allows predictions to be made about how a population will change. We call a scientist that studies demography a demographer. Okay, there are three key features of populations: the size, the density, and the dispersion. Size is basically the number of individuals that are in the area. How we determine size, there are things like birth rate and death rate. Okay, we can talk about birth rate as natality, death rate as mortality. It's basically how many individuals are born versus how many individuals die. When we calculate the birth rate minus the death rate, we talk about the rate of natural increase, or how much the population is either growing or declining based on these figures. Here you can see certain countries as they change versus their birth rates and death rates. And you can see the type of change. A rapid growth means that one is very, very small up at the top, but exploding towards the bottom. Check out Kenya on the left side of the graph here. Slow growth is the United States, so our population is still growing. And then zero growth or a decrease in population is for a country such as Italy, where you see in the middle here, it has a larger number of individuals versus how many are being born. Let me move my screen here out of the way, and you can kind of see that area. I'll move it back down here. You will see these figures. One thing I want you to pay attention to is that in this area you can see where the numbers correspond to a percentage of individuals. So in this area you have individuals who are 0 to 4 years of age, all the way up to 8% of those individuals. Now, the biggest thing here is that you need to pay attention to the male and the female side. If I were to ask how many individuals are from 0 to 4 years of age, if you're talking specifically about females, it would be 8%. But if you're talking about all the specific individuals in that range, it would be 16%, because you need to include both sides here. Do not get confused about that question. There will be questions that ask how many individuals range from 0 to 4 years of age, and you will need to answer 16%, because you need to include both male and female. This is a rapid growth, a slow growth, or no growth, and this is a decayed or decreasing growth curve. Okay, another key feature of populations is density, or the measurement of population per unit area or volume. Basically, the population density is the number of individuals divided by the unit of space. So how many people are packed into a certain area? When we think population density, I always give the examples of, think New York City versus somewhere out on a farm in rural North Carolina. New York City has a lot more people per square mile than does a farm. And how can we affect density? Well, we have the two types of immigration. We have immigration with an I, which is movement of individuals into a population. So say somebody moves from somewhere to somewhere, coming into somewhere, they are an immigrant with an I. We can also talk about immigration with an E, which is movement outside of a population. So when you move away from somewhere, you are an immigrant with an E. There are several density-dependent factors. These are factors that will affect and change a population based on density. Things like biotic factors in the environment that have an increasing effect as population size increases. Think disease, competition, parasites. Disease is obviously going to increase the more individuals are packed into an area. And then there are density-independent factors, which are abiotic factors in the environment that will affect the population regardless of their density. So things like temperature, weather, and certain natural disasters. You can see here how all of these things affect population both positively and negatively. Here you can see types of population dispersion. We can talk about clump dispersion, like schools of fish, uniform dispersion, where everybody is just spread out in uniform, and then there's random dispersion where everything is just all over the place. Dispersion specifically describes the spacing of organisms relative to each other, and you can see the three types that I just discussed. How do we measure populations? Well, population density equals the number of individuals in a given area or volume. Basically, we count all the individuals in a population. That is one way. Or we can estimate by sampling. We can say that, for example, there are 20 people in this classroom. There are 10 classrooms on this hall. Therefore, there must be 200 people on this hall. We can mark and recapture method, where basically we tag somebody and then we capture a bunch more individuals and see how many individuals it takes before we capture that person that we marked. And how do we grow? There are idealized models that describe two kinds of population growth. One is exponential growth and one is logistical growth. Carrying capacity is the maximum size that a population can support by all the available resources, and there can only be as many organisms as the environmental resources can support. Think about only having a finite amount of water. You can only have the number of individuals that can use that water. We can't have more individuals, otherwise we will run out of water and people will die. Think back to the tragedy of the commons that we discussed in Unit 3. Here's an example of exponential growth. Notice that each time it is multiplied by an exponent. You can see that the 2 has an extra exponent on it on the mathematical side, and then you can see the type of curve that is associated with exponential growth on the right. We call this a J curve. Any curve that gives this type of, or has this type of look to it, is a J curve, or indicates that something is growing exponentially. Conversely, a logistic growth is exemplified by this type of curve, which we call an S curve, which shows the carrying capacity of something. Factors that'll limit growth rate: declining birth rates or increasing death rates are caused by several factors, things like food supply, the buildup of toxic waste, disease, predation. A lot of times there are booms and busts in a population, so when resources increase, you tend to have an increase in a certain population, which allows another population to increase based off of the more available food source. One big one here is the snowshoe and the hare. One that we'll talk about are wolves and deer, or predator and prey when we play our predator-prey game. You can see how as the snowshoe hare population increases, you see a jump in the lynx population here, and then once the lynx has grown to a maximum height, they start to eat all the hare, and thus the hare population will decline. And then it goes on, so forth and so on. As the hare population declines, there is less food for the lynx to eat, and so some of them die off. There are several reproductive strategies to increase populations. There are the R strategies, which include a short lifespan, small body size, they reproduce very quickly, have several young, and very little parental care. When you have so many young, it's hard to care for so many babies. We think insects, weeds, bacteria here. Basically, they want to take over everything by increasing numbers. You have the K strategies, which is where we fall, which generally have long lifespans, larger bodies. We reproduce slowly, have fewer young, and provide parental care. They're more invested in getting quality out of quantity here. Age distribution is calculated by the number of males and females in each age group of a population, and it's used to predict future population growth. Think back to the graphic that I showed you earlier about population growth in countries. Here we see it again. When there is an increase number of individuals in a lower form here, you can see where I'm highlighting the cursor, it tends to mean that there will be an increase in population size. A exponential growth curve, or a J curve, grows at a rate about 80 million a year on Earth for humans. So we're talking about human population growth here. And why doesn't environmental resistance take effect? Well, humans are adept at altering their environment. We can change things. We've invented structures, air conditioning, heat, all of these things that have helped us survive things that once plagued our population. Basically, our technological advances have allowed us to survive much more efficiently. The human population, here's some facts about it, has doubled 3 times in the last 3 centuries. There's about 6.1 billion when this PowerPoint was created. There's around 7.3 billion now, and could reach about 9.3 billion by the year 2050. Improved health and technology have lowered death rates and allowed us to stay alive a lot longer. And here we can see just how much the human population has increased over time. That's all for today. We'll get more later.